We have a pretty cool podcast today. It's about controlling shockwaves with plasma generators. So shockwaves are cool, plasma is cool, so together they're like Sub-Zero. And shockwave boundary layer interactions are what we're looking at today, and they're exactly what they sound like. It's when a shockwave interacts with a boundary layer and creates its own flow physics, and it changes it. And that can be good, but it can also be bad, and often it's quite bad. So for example, in last week's podcast, we were looking at the flow entering a turbofan's inlet and how at high mass flow rates, shockwaves force the boundary layer to separate. That can happen and quite often does happen. And that is usually quite bad because it changes how efficient the intake is and then the rest of the engine. So today, we're looking at how to control the boundary layer shockwave interaction, and in particular with plasma generators. So a few weeks ago, we went through using plasma generators to control the flow over a train. And that was pretty cool. We found some really cool results there. And now we're looking at how to use plasma to control this shock and hopefully for our benefit. So just a quick recap, a plasma generator is a fairly simple device. You have two electrodes separated by a dielectric material. And when we went through this in last podcast 169, so I don't want to go too much into it here, but I'll just say that when you apply electricity to this broken circuit with the dielectric material between it, plasma forms. And that plasma is often quite hot, but in that podcast from a few weeks ago, we saw that the temperatures were so low that you might even be able to touch it without getting burnt. So that's pretty cool. And to see if it is even possible to use plasma to control a shockwave, we're looking at a paper called, if I scroll up here, Investigation on Supersonic Flow Control Using Nanosecond Dielectric Barrier Discharge Plasma Actuators. And that is just fancy talk for controlling shockwaves with plasma and using this plasma actuator, this plasma generator to do it. And this is open access. You can find it in the link below. So in figure 1, they give a diagram of the shockwave boundary layer interaction that forms when supersonic flow passes over a shock generator. So the shock generator is quite simple. I mean, it's like literally just a flat plate, and then some distance away, there is a wedge. And this wedge effectively reduces the cross-sectional area that the flow goes through and introduces like this object that the flow has to go around. And then we get shocks forming because the flow is supersonic to begin with. And the important thing to note is that the boundary layer forming on the flat plate cannot interact with a shock. So it's a perfect storm. And it can now interact with the shock. And in order to understand the shockwave boundary layer interaction, there are a few aspects that we need to cover, and it might not make much sense right now, but once we cover them, you'll understand, okay, this is why we need to know about this stuff. So let's go through that quickly. And so in figure 1, we have the separation shock. Let me zoom in a little bit here so we can see a bit more what is going on. We have the separation shock, which is just here in this purple. And this is a few shocks related to the boundary layer separating. So we can see here that with the boundary layer, which is denoted by this solid black line. We then have the incident shock up here, which is from the shock generator. That's what is creating this incident shock. This shock shoots down at an angle and past the boundary layer separation. I probably shouldn't say actually that it's shooting down because it's a standing shock from what I can tell. But anyway, we have then the reflected shock, which is behind both of these shocks. And it's a little bit weird because it is a different kind. Like it travels faster than the other shocks because the incident shock heats up the air. So that allows this reflected shock to actually travel faster. And that's why we also get some of this bending here a little bit as well. So we have the max stem, which is just here. And this is where this is the overlapping of a couple of shocks. Now, these features are all well and good, but it is the interaction of these features, and namely at the point at which the incident shock, the max stem, and the reflected shock meet. That's the important part. So around this region where this max stem is, this is called the triple point. And the authors say that the distance between the triple point and the surface greatly determines how much the shock waves and boundary layer will interact. So the further away it is, I guess the less it will interact because the shocks are further away and where they're interacting with the boundary layer. Now, one thing that is interesting actually is that there is a separation bubble that can form with this boundary layer. And if you've listened to our other podcasts for a while, you know that I have a kind of love-hate relationship with separation bubbles. They're great in that they're really interesting, but they're terrible in that they are really hard to simulate with CFD. And we often see that these bubbles occur at transitional Reynolds numbers. So between about 50,000, actually theoretically in air, around 50,000 is the lower end that you can actually get them forming. Below that, you can't really get them forming. And then up to about 200, 300, 400,000 in the Reynolds number is when we can start to go past that. So that range between 50,000 and 400,000 in the Reynolds number is where we get these separation bubbles usually forming. But here, we actually get the separation bubble forming for a slightly different reason. It's not really transition based. It is actually caused by the shockwave bandular interaction, creating an adverse pressure gradient, which then makes the bandulae separate, and then it reattaches. So it is a little funny to see a separation bubble here because just how different the free stream conditions are compared to subsonic flow. And arguably, what most of the literature is talking about is at the subsonic conditions. So to see it here is a little bit unusual, but it definitely can happen. So this bandulae separation can wreak a bunch of problems, and one of them is an increase in drag, another one is a reduced pressure, and these can reduce the performance of intakes, for example. Hence why controlling this bandulae is important. And the authors detail another study by a geezer called Webb, and apparently this study showed that a plasma actuator placed upstream of the shocks increased the energy in the bandulae and reduced the separation length. So he or she found that plasma actuators can positively affect the bandulae, and this is very beneficial. So in this study, the authors are focusing on how the length of the plasma actuator affects the separation length and shock position. So is more plasma generator better, in other words? Should you have a longer one, a shorter one, what? So to do this, they are using URAN CFD, and I should mention before we get into the CFD that this is actually a really nice CFD setup. I was really impressed with it. Probably one of the better ones I've seen in a long time. But anyway, the free stream flow is 2.5 Mach number, and the shock generator was a wedge with a 14-degree angle, so that angle between the horizontal and this angled surface here. They used the K-Omega SST Thermos model, and the two test cases are given in figure 4A and B. So let's scroll down to those ones. So we have two test cases with the flow coming straight in, and then we have one actuator, which is the top one here, that has a length of 90 millimeters, and the second one has a length of 110 millimeters, and they start at the exact same point, but just the longer one goes a bit further downstream, that's all. And they're like located the same distance from the sidewalls and the top. So in terms of their location with respect to the shockwaves, in figure 4C, we see that the shorter plasma actuator generator, so the shorter plasma generator stops before the shock hits it. So we can see that it stops about here, whereas these shocks coming down, they end just before it. But the longer plasma generator continues and is hit by both the incident shock and the separation shock. So that's a little bit different in potentially how they will operate, because they have different conditions that they're operating under. So that is without the plasma generator on, and with it on, the shocks might move, and we'll have to wait and see what will happen. Now let's move on with their grid independent study, because they did a really nice job here. So down here we can see what they've done, and this is figure 5A, and they've tested a few different measures ranging from 2,300,000 to 4,800,000. So it's a really nice spread here. It's not like 2.3 million to 2.4 million, it's 2.3 to 4.8 million. They've done a good job here. And to see how the grid converged, the property they looked at was the pressure. And all the grids gave very, very similar results. So you can see these lines are all bang on each other. So we can say that the grid independent study was a success, and it was very well done. One thing that I'm not sure about though is where the pressures were taken. I don't think that is a big issue here, because while it would help remove some doubt, the fact that the pressure rose quite a lot and it changed quite a lot across this range tells us that this pressure was taken in a region of high activity and not in the free stream flow, like far away. So the way the pressure increases and where it increases, I would say that the pressures were taken along the plasma actuator, maybe a few millimeters above it. So I'm quite impressed with the grid independent study here, and I can say that it's probably pretty good. In addition to this, they also had some validation data to compare their results to, and that's given in figure 6. And again, this is really nice. So they have the pressure from the same area as investigated with the grid independent study, and now they have the experimental data from another study, and it matches very nicely. Like there's a little bit of a difference, but the experimental data was at a Mach number of 2.8. The CFD was at a Mach number of 2.5. So there was a little bit of difference there, but still they get the exact same trend. So that's quite impressive. In figure 6B, we see the shockwaves from the CFD in the top, and then from the Schlieren, which is in the bottom. And Schlieren is just an experimental process where you literally shine light into your flow, and then you have like this, like they call it like a knife edge, which then cuts the flow, the light, sorry, and then it highlights where the shocks are by changing how much concentration there is in the light. Anyway, we see that in the bottom part here from the experimental results, and the CFD matches the experimental results really closely. Even the angle of the incident shock, which was 33.2 degrees in the experimental data, was 33.2 degrees in the CFD as well. So it's really, really close. So I think we can say that CFD is well validated. And I mean, okay, there are some minor differences in the pressure data between the CFD and the validation data, but that could also be just uncertainty in the experimental data as well, because we don't have any error bars here either. So that is not just the CFD, it might also be the experiments as well that are off. So I quite like the CFD that it did a good job here. And given the grid independent study and the validation, I think the CFD is around a 9 out of 10. Overall, it's really good. So we can trust these results quite nicely, I think, quite a lot, I think. So let's move on with the results. So in figure 7, we see the friction factor, so figure 7 here, the friction factor along the boundary layer and the effect of the plasma generator on it. So first, this is for the shorter of the two plasma generators, 19 millimeters. And now the friction factor is an important factor because it helps understand the friction at the wall. But it is even more important here because it also helps us show where the separated flow is. So let me explain why. So when the friction factor is negative, the flow is deemed separated, and as such, we can see the exact effects the plasma generator has on the flow. And the reason why when it's negative, it's separated, we consider it, is because that means now the flow is moving in the opposite direction. And that's what happens in separation bubbles. When you have the flow detaching and then reattaching in that separation region, the flow usually goes the other way. So when we have a negative friction factor here, we can be quite certain that is where the separation bubble is. So that gives us a very quantitative way of telling where this bubble is occurring. So the red dashed line is for the generator on, and the black dashed line, the black solid line is without the generator at all. Now we see that the plasma generator greatly affects the flow separation, and in quite a strange way actually. So the pressure actuator didn't prevent the separation. In fact, arguably, it made it worse because the flow separation occurred farther upstream and stayed detached overall for longer. So in fact, the plasma generator almost reduced the length of the separation bubble because we can see that the red line is negative here. It starts detaching sooner, and then it's negative, and it starts to go to the 0 line. But then as it touches the 0 line, it then detaches again. And then it pretty much follows the exact same path as the black line. So while it may have had the chance to reduce the bubble length, it just made it longer in total and actually divided the bubble into 2 bubbles really. So the authors say that the flow ended up separating again because the energy in the boundary layer still wasn't enough from the plasma generator. And we'll look at that a little bit later with the boundary layer profiles. But in this particular case, the plasma generator effectively did more harm than good in the separation region. It made it bigger. But it's not all that bad because this top part of the figure, we can see that pretty much as soon as the flow encountered the plasma generator, the friction factor dropped. So that means that the drag arising from the friction in this region is actually lower with the plasma generator on than with it off. So that means that the friction drag should be a little bit lower. And that's actually funny because the additional separation region will also reduce the friction drag as well, because we have even more negative friction factor here, which again eats into the friction drag that we'll usually get and reduce it. Now the question becomes is the plasma generator with it on, is that using more energy than the drag reduction that we get, or is it using less? If it's using less, then it means that the plasma generator is actually better to use to actually reduce the drag. If it's using more, then it's actually worse. It's not as efficient to have the plasma generator on, and we should just get rid of it. So from these results, while the plasma generator did not do what we wanted it to do in terms of reduce the separation length, it did have a positive effect on the drag, which that's something to note, and we can use it in other applications. But let's move on. And also, I should also mention, compared to the other study by that Geezer Webb, that study showed that the plasma generator actually reduced the length of the separation here. For some reason, this plasma generator didn't. So that's a difference there, which is actually good. It means that we have quite a few options to choose from. And it shows that increasing the plasma generator length changing the plasma generator may have a better effect, and we can swap and change to determine what we want to do. So in figure 8, we see the same friction factor idea as in figure 7, but for the longer plasma generator. And interestingly, we see the same trends here. So the plasma generator on, the longer one this time, increased the length of the separation bubble again, and that isn't good, but it also reduced the friction factor upstream of the separation bubble. And in the separation bubble region, the friction factor was also reduced quite a lot more, which means that, again, this plasma generator, for some reason, this configuration with these flow conditions reduces the drag and doesn't reduce the separation region. So those are exactly what we saw for the shorter plasma generator. But one main difference between these two is that this larger one didn't create two separation bubbles. You know how in the other one, the shorter plasma generator created two small bubbles. This one just had one long one. And there was a chance for the plasma generator to actually divide the bubble into two. But once it got close to the zero line, it then went negative even more again. So it prevented that from happening. And so the separation bubble is just bigger here and hasn't been divided into two small bubbles. But what about the temperature though? Because in the podcast from a few weeks ago, podcast 169, the plasma was pretty cool at some points, and it wasn't really hot enough to even potentially burn you at some points. How hot is it here though? I want to compare them. So if in figures 9 and 10, we see the temperature across the surface with the short and long plasma generators respectively. Now I should note that we see two different dashed lines in these figures. The black dash one is for when the plasma generator was toggled on for just 100 microseconds, while the red one is with the plasma generator on for 200 microseconds, so twice as long. So first of all, the temperatures were around 400 to 450 Kelvin, which is much hotter than those plasma generators we saw in podcast 169. And at these temperatures, you could cook a steak or something. Like you would get burnt by it pretty bad. So that is quite different to what we saw a few weeks ago. But interestingly, the amount of time the plasma generator was on for didn't really affect the maximum temperature, which I find a little bit strange. I mean, if you had the plasma going for longer, I would expect the temperature to increase, but not here. And I don't know, maybe it's because there was like this temperature saturation happening. Anyway, another thing to note is that the extra length in the plasma generator had no effect on the temperature until the additional length was encountered. So we can see here, if I zoom out a little bit, the graphs are almost identical until we get to the point where the longer plasma actuator continues. And then from there, the temperature increases quite a lot. So there are literally no upstream effects from this larger plasma generator. And what I mean by that is that the additional length didn't affect the temperature upstream. And that kind of makes sense because the flow is supersonic. But then this plasma I don't know what the speed of sound is in this plasma, so I don't know if that is supersonic. So it may or may not be in this region. Anyway, another thing to note is that even without the plasma generator, when we start to get some shocks forming, the temperature increases, and that is expected because the shocks are not isentropic, which means that the processes are not reversible. And that is primarily because they convert some kinetic energy into some heat. And that's why we get this high temperature forming in this separation bubble region. And actually, just on this point of isentropic and thermodynamics and stuff, we all know that in reality, pretty much all of our machines that we have are nowhere near 100% efficiency. For example, a car with an internal combustion engine is like 30% efficient or about that. And so we continually just expect that whenever we use something, there will be some loss. Well, on that note, I actually think I've broken the matrix because in winter, I actually have something that is 100% efficient. So when I'm feeling cold in my office, I just put on a simulation on my computer, and now that computer puts out heat. So the operation of the running simulation is not 100% efficient because you get the simulation plus the heat, and we don't really want the heat. It's just the simulation that we want. But in winter, I actually want that heat to warm my office as well. So technically, my computer is running at 100% efficiency because everything the computer is doing, I want. So I want the simulation, I want the heat it gives off, which is usually the inefficient part that we consider. So I'm kind of one step ahead of thermodynamics here. But let's get back to this paper. So in figure 11, we see some really cool pictures of the temperature along the surface with and without plasma generators. Let's zoom into the top figure here because this is without the generator. Here we go. And this picture is really beautiful. I mean, like, this is textbook in terms of shocks. They're really crisp. You could put this in a textbook and use this to teach shock waves is just beautiful. And we see that as soon as shocks occur, right after that, we get much higher temperatures. So anytime we get like this line, before and after, there's a higher temperature. And we actually get reflections of the shocks back a little bit as well, it seems. But one thing that I'm not sure about actually is behind this wedge. So if you look here, the temperatures jump up quite a lot, and I'm not exactly sure why. I mean, I don't think there is a shock here. I can't see anything that would suggest that. So I don't know why the temperature increases here, and it's by a lot. Anyway, in the figures below, we see the temperatures in the flow with the two plasma generators and over the course of being activated for 15 microseconds, 60 microseconds, and 100 microseconds. And from what I can tell, the amount of time the plasma generator is on makes absolutely no difference to the temperature in the flow. I mean, we can see comparing this one to this one and this one, they all look pretty similar, if not identical. So that's interesting. Again, the temperature is not really affected by how long the plasma generator is on for. Now, in figures 12 and 13, let me zoom out and go to those ones, we see the effects of the plasma generator on the shocks, and they really do affect them quite a lot. So this is for the smaller generator. This is for the larger generator. They both have similar effects. Let's zoom into this one first. So, for example, we can see that the separation shock, which is the last shock really in the system, this one here that I'm pointing to, all the way down here, is being bent down, and it's no longer fairly straight. So this one is here, is a bit straighter, but it gets more and more bent as we go down, and even like sort of crimping here. So there's like two sort of shocks, like there's bend here in it. And also between the separation bubble and the shock, so the separation bubble is blue, and then there's green here. As we go down, increasing the amount of time the generator is on, we're getting a lower and lower velocity happening here. So it's kind of like maybe the separation region is growing. Once we get past this region, I can't notice too much of a change though. But the fact that this plasma generator is bending this shock and is changing how much flow is separating is pretty cool. I mean, I can't bend a shock wave. Actually, I probably could. Like if a shock hit me, maybe it would. I don't know. Would it? Actually, I might get hurt. I don't know. Do you think I would get hurt? I'm not sure what the pressure is in a shock wave. I should probably know this. That's something for me to look up. But anyway, it's pretty cool that these generators can change the shock waves and bend it. Let's move on to figure 14. So in figure 14, it shows the separation bubble, and the black line is kind of the point at which the flow goes from subsonic to supersonic. Above this line, it's supersonic. Below this line, it's subsonic. And the plasma generators increase the size of the subsonic region. So we can see here, this is for no generator. The height of this region is about 6.2 millimeters. With the generator, it goes up to about 12.1 millimeters, and it really fans out a lot more. So one final thing that is interesting to look at is the boundary layer profile, which is the velocity of the flow as you move away from the wall. And these boundary layer profiles are taken like halfway along the plasma generators. And the plasma actually reduces the velocity in the boundary layer here and makes the profile more laminar. A little bit surprising. And this is different to many applications where the force of the plasma imparts on the flow, increases the velocity in this region, and actually makes the boundary layer profile more turbulent like. So this is the opposite here. But given the results we've seen so far, it actually makes sense that the plasma is reducing the velocity in this boundary layer and making the profile more laminar, because remember how we saw that the plasma generator makes the flow separate earlier? Well, it is almost a guarantee that this occurs because the boundary layer is more laminar now. The velocity of the wall is lower, so it can't resist adverse pressure gradient as long. So that makes complete sense that the plasma generators are reducing the velocity of the flow near the wall, and that as a result is making them separate sooner. Alternatively, compared to that Giza-Webb's results where they found that the plasma generator actually reduced the separation region, maybe that plasma generator increased the velocity of the boundary layer profile in this region. So that is just maybe oriented in a different way, or has a different plasma generator to it, or different strength, maybe something like that. So we can conclude that for these particular generators, which operate in a pulsed fashion, it definitely changed the flow separation characteristics, making the flow separation sooner and over a longer length. The shorter plasma generator also made 2 separation bubbles out of 1, and the plasma also heated the flow up quite substantially, and it altered the shock waves. So while these plasma generators didn't suppress separation, we did see that they negatively affected it, and just not that great in this particular way. But there are some potential applications for this if you wanted to reduce the friction drag, for example. And the other plasma generators that we saw from Webb, they could be used to actually reduce the separation region. And that is good. We have options at least. So that brings us to the end of this podcast. If you'd like to, make sure to like and click the subscribe button or follow button, whichever platform you're on. And if you want to learn how to use OpenFOAM, take our course and link below. It's a really good CFD software. And if you want to make your experiments 2 to 4% more accurate, get yourself an Amazon Hawk. You can find a link below. And in that link as well, we go through the math as to why there is almost certainly a 2 to 4% error in your experimental data, and you don't even know it. So that brings us to the end of this podcast, and I'll see you next one. Peace out, amigos.